Welcome, dear listener. You've found your way to Dreams of Gravity, and we're so glad you're here. Wherever you are right now, whatever kind of day you've had, whatever thoughts are still spinning quietly at the edges of your mind, you can let them go. Set them down gently, like a stone placed on the shore of a quiet lake. You don't need to carry them any further tonight. They'll be there tomorrow if you need them. But right now, they can rest. Make yourself comfortable. If you're lying down, let your body sink a little deeper into wherever you're resting. Notice the weight of your arms against the mattress or the floor or the cushion beneath you. Feel the soft pressure of whatever surface is holding you up. If there's a blanket nearby, pull it a little closer. Wrap yourself in its warmth the way the earth wraps itself in atmosphere, a thin and gentle layer between you and the vastness outside. Take one slow breath in through your nose, filling your lungs all the way to the bottom, and let it out slowly, completely, until your chest is quiet. And then breathe again, naturally, without effort. There's nowhere to be, nothing to do. No decision to make, no message to send, no task to remember. For the next little while, everything can wait. The world will continue without your attention for a few hours. It always does, every night while you sleep. The stars don't need you to watch them. The universe doesn't need you to keep up. It will still be here when you wake. Tonight, we're going to drift together. Out past the clouds, past the cool and quiet stratosphere, past the moon hanging silver in the dark, past the familiar shapes of planets in their steady orbits, into the vast and ancient silence of deep space. And there, in that silence, we're going to talk about the most powerful explosion the universe has ever been known to produce. An event so extreme, so incomprehensibly energetic, that our instruments were overwhelmed just by the echo of it arriving from nearly 2 billion light-years away. But we'll get there gently. There's no rush. The universe itself is in no hurry. It has been unfolding for nearly 14 billion years, and it will continue for billions upon billions more. A few quiet hours, drifting through ideas together, is nothing to the cosmos. It is barely a breath, barely the flutter of a single eyelash in the long, patient night. So let yourself breathe, and let's begin. The universe, as far as anyone can tell, began not with a whisper, but with something that had no sound at all, because there was nothing yet to carry sound. No air, no space, no distance between one point and another, no before and no elsewhere. Everything that would ever exist, every galaxy and star and planet, every ocean and mountain and living thing, every thought that any conscious mind has ever had or will ever have, was compressed into a single point of infinite density, smaller than anything you could ever see or touch or imagine. And then, in an instant that scientists call the Big Bang, it expanded, not like a bomb going off inside a room, more like the room itself suddenly appearing from nothing and growing in all directions at once, carrying everything inside it outward, the way the surface of a soap bubble grows when you blow gently into it. Except that this bubble had no outside, no surrounding space for it to expand into. It was space itself that was expanding. It still is. That was about 13.8 billion years ago. And the universe has been expanding ever since, slowly, steadily, like the long and ancient exhale of something that had been holding its breath for an eternity before the first moment of time. In the first fractions of a second after that beginning, The universe was a blinding, unimaginably hot sea of pure energy. The temperature was so extreme that not even the basic building blocks of matter could form. There were no protons, no neutrons, no electrons. Just raw, furious energy, churning and swirling in all directions. As the universe expanded, it cooled, the way a cup of tea cools when you leave it on a window ledge. And as it cooled, the first fundamental particles condensed out of the energy like droplets of water forming in cooling air. Protons and neutrons appeared. And in the first few minutes, some of those protons and neutrons bound together to form the simplest atomic nuclei. Hydrogen, mostly, and a little helium, and tiny traces of lithium. That was it. That was the entire periodic table of the early universe. 2.5 elements. A chemical vocabulary so limited it could barely whisper a single syllable. And yet, from those 2 humble elements, the universe began to write the most extraordinary story ever told. By the way, I wonder, where are you watching from tonight? Which city and what time of day is it for you right now? Are you tucked in somewhere warm with the quiet sounds of night around you? Maybe a distant car, or rain on the window, or the soft breathing of someone sleeping nearby. Or perhaps it's still evening where you are, and the day is just settling down, the last of the daylight fading outside. Wherever you are, I hope it feels peaceful. I hope the light is low and soft, and the air is comfortable, and your body feels heavy in the good, restful way. We're glad to have you here, in this small, gentle corner of the cosmos, traveling through space together. And now, let's continue our journey. After those first minutes of nucleosynthesis, the universe spent about 380,000 years in a strange state. Too hot and dense for atoms to fully form, a glowing fog of particles and radiation, opaque to light the way a thick cloud is opaque to sunlight. And then, as the universe continued to cool, something remarkable happened. Electrons slowed down enough to be captured by the atomic nuclei. The first complete atoms formed. And suddenly, the fog cleared. Light could travel freely for the first time. The universe became transparent. That ancient light, the first light ever to travel freely through space, is still out there. It has been traveling ever since, cooling and stretching as the universe expanded, until today it fills the entire cosmos as a faint, uniform glow of microwave radiation. We call it the cosmic microwave background, and we can detect it with our radio telescopes. A whisper from the infancy of the universe, a faint echo of the first moment the cosmos became see-through. It is the oldest light we will ever be able to observe. Looking at it is looking back as far as it is physically possible to look. After that clearing of the fog, the universe entered a period that cosmologists call the Dark Ages. Not dark in a dramatic sense, simply dark in the literal sense. There were no stars yet. The universe was filled with vast, slowly drifting clouds of hydrogen gas, cooling and expanding, lit only by the fading afterglow of that initial light. It was quiet and dark, and would remain so for hundreds of millions of years. And then, gravity, that invisible and infinitely patient force, began its work. Clouds of hydrogen began to drift through the newborn universe. They were not rushing. They were floating slowly, the way fog moves through a forest in the early morning, the way smoke drifts from an extinguished candle on a still night. But gravity, always pulling, always gathering, began to draw these clouds together. In some places, the gas was very slightly denser than in others. Tiny fluctuations, quantum ripples from the first moments after the Big Bang, stretched to enormous scales by the expansion of space. And around those slightly denser regions, more gas gathered. Slowly, over millions of years, pockets of gas grew denser and denser. They began to collapse inward under their own weight, the way a slow and casual breath becomes a deep, purposeful inhale. And as the gas compressed, it heated up. And at some point, deep inside one of those collapsing clouds, the temperature and pressure became so extreme that hydrogen atoms began to fuse, merging together, combining, releasing enormous amounts of energy in the process. A nuclear fire ignited. A star was born. Imagine that moment. After hundreds of millions of years of darkness and drifting and quiet, a light switched on. A single star, burning in the black, its light reaching outward in all directions for the first time, pushing back against the ancient dark. It must have been, in some way we can never directly observe but can try to feel, a remarkable thing. The universe had made something luminous, something warm, something that could shine. Those first stars were enormous, far larger than our own sun. Some of them may have been hundreds of times more massive, colossal, brilliant, ferociously hot. Scientists call them population 3 stars, and they burned through their fuel so quickly that they lived for only a few million years. In cosmic terms, a few million years is almost nothing, barely a moment, like a match struck and extinguished in an otherwise long and quiet night. But when they died, they didn't simply go out, they exploded. And in those explosions, in the tremendous heat and pressure of a dying star, heavier elements were created. Carbon, oxygen, nitrogen, silicon, iron, all the atoms that would one day make up planets and oceans and mountains and living creatures, all the atoms that make up you. This is one of the most humbling discoveries science has ever made. Every atom in your body, every atom in the hand resting on your chest right now, every atom in your eyelashes and your heartbeat, and your slow and steady breath, was forged inside a star. Not metaphorically, not poetically, chemically, measurably, verifiably. Your iron was made in the core of a massive star that lived and died billions of years before the Earth existed. Your calcium, your carbon, your oxygen, all of it cooked in nuclear furnaces and flung out into space in colossal explosions, and scattered across the galaxy, and gathered together by gravity into new clouds, and condensed into new stars with planets around them, and deposited on the surface of a young world, and dissolved into oceans, and incorporated into chemistry, and eventually, after billions of years of slow and patient transformation, assembled into you. When you breathe tonight, you are breathing atoms that have been part of stars. When you sleep, you carry the universe inside you, not as a sentiment, as a physical fact. After those first great stars exploded, their enriched remnants scattered outward like seeds on the wind. And gravity, again patient and unhurried, began gathering those enriched clouds together. New stars formed, smaller, more stable, longer-lived, stars more like our sun. Around some of those stars, the leftover material, the dust and gas and microscopic grains that didn't make it into the star itself, began to clump together, slowly, over millions of years. Grains of dust stuck to each other, building up into pebbles, and pebbles into boulders, and boulders into planetesimals, the embryonic building blocks of planets. and planetesimals collided and merged over and over until they became full-grown worlds. Some of those worlds found themselves at just the right distance from their star, not too hot, not too cold, in the narrow band that astronomers call the habitable zone, where liquid water can exist on the surface. And on some of those worlds, in just the right conditions, perhaps rarely, perhaps more commonly than we imagine, something extraordinary happened. Chemistry became biology. Simple molecules began to organize themselves into structures capable of copying themselves. Life began. And life, over billions of years of slow and patient evolution, became complex. And complexity eventually became consciousness. And consciousness became curiosity. And curiosity built telescopes. But tonight, we are following a different thread of the story. Tonight, we are following the story of violence. Because the universe, for all its vast and meditative silence, for all its dark and quiet spaces, is also capable of producing events of almost incomprehensible destructive power. And the most violent thing the universe has ever been known to do is something called a gamma-ray burst. To understand a gamma-ray burst, it helps to first understand how stars die. And to understand that, it helps to understand how they live. A star is, at its heart, a war. A constant, ongoing battle between two forces that never stop pressing against each other. On one side, gravity, the inward pull, always trying to collapse the star, to crush it down into something smaller and denser, to reclaim all that diffuse gas and fold it back into a single point. Gravity never rests. It never weakens. It applies its squeeze every second of a star's life, patiently waiting for the fuel to run out. On the other side, the energy of nuclear fusion, the outward pressure generated in the star's core, the fire that pushes back, that holds the star expanded like a balloon, that keeps gravity's squeeze at bay for as long as the fuel holds out. For as long as a star has hydrogen in its core, these two forces are balanced. The star sits in a state of equilibrium, held up by its own fire, shaped by gravity's pull into a near-perfect sphere. It shines steadily, patiently, sometimes for millions of years, sometimes for billions. Our own sun has been in this balance for about 4.6 billion years. It will remain so for roughly another 5 billion years. 5 billion years of quiet, steady burning. From our perspective on Earth, the sun seems almost motionless, a bright and benevolent presence in the day sky, warm and familiar and constant. But the sun is not still at all. On its surface, storms the size of Earth rage continuously. Enormous loops of magnetized plasma, called prominences, arc thousands of kilometers into space and fall back like slow, glowing waves. Sunspots drift across the surface in patterns that wax and wane on an 11-year cycle. Solar flares erupt periodically, launching bursts of radiation and energetic particles outward through the solar system. The sun is furious and ancient and alive with activity. And yet, from 150 million kilometers away, it looks like a calm and steady lamp. But all stars eventually run out of fuel. The hydrogen in the core is consumed. The nuclear fire begins to falter. And when it does, gravity begins to win. For a star like our sun, the end is relatively peaceful. As the hydrogen in the core runs out, the core contracts and heats up, and the outer layers expand enormously, puffing outward into a vast red giant. The sun, in its red giant phase about 5 billion years from now, will expand to perhaps 100 times its current size. possibly engulfing Mercury and Venus and scorching the Earth beyond recognition. But eventually, even this phase ends. The outer layers drift away into space, forming a glowing shell called a planetary nebula, a beautiful, slowly expanding ring or cloud of illuminated gas drifting peacefully outward. And the core that remains, the collapsed remnant of the star's interior, is a dense, slowly cooling object called a white dwarf, about the size of the Earth, but with the mass of the Sun, dense enough that a teaspoon of its material would weigh a few tons, slowly fading over billions of years, like an ember cooling in a fireplace that will never be stoked again. It's a quiet ending in the grand scheme of things, a sigh, a slow release. But for stars much more massive than our Sun, stars 10, 20, 50 times heavier, the end is not gentle. When the nuclear fuel runs out in the core of one of these giants, something very different happens. The core collapses, not gradually, catastrophically, in less than a second, less time than a single heartbeat. The core, which was previously held up by the pressure of nuclear fusion, suddenly has no outward force to resist gravity, and gravity crushes it in an instant, from something the size of the Earth down to something roughly 20 kilometers across. A city-sized sphere of matter so dense that a single teaspoon of it would weigh hundreds of millions of tons. The protons and electrons in the original atoms are crushed together under the pressure, combining into neutrons. What's left is called a neutron star, the densest object in the universe aside from a black hole, spinning rapidly, pulsing with magnetic fields of almost inconceivable strength. But the story doesn't end with the core. When the core collapses, the outer layers of the star, all those vast shells of gas and plasma, come crashing inward. They hit the surface of the newly formed neutron star and rebound with tremendous force, launching a shockwave outward through the remaining layers of the star. That shockwave, combined with a flood of neutrinos streaming out from the neutron star, tears the star apart. The outer layers are hurled into space at a significant fraction of the speed of light. For a few weeks, the explosion, called a supernova, outshines an entire galaxy of hundreds of billions of stars. A supernova is one of the most spectacular events the universe produces. The energy released in a typical supernova is roughly 10 to the power of 44 joules, more energy than our Sun will emit over its entire 10 billion year lifetime. Most of that energy, strangely, is carried away not by light, but by neutrinos, ghostly particles that barely interact with anything, passing through matter as easily as sunlight passes through glass. Billions of neutrinos from ancient supernova pass through your body every second, day and night, without interacting with a single atom. Throughout recorded history, a handful of supernovae have been bright enough to be seen with the naked eye. In 1054 AD, Chinese and Arab astronomers recorded a new star appearing in the sky, so bright it could be seen in daylight, visible for 23 days. That explosion, now about 6,500 light-years away, left behind a glowing cloud of gas called the Crab Nebula, still expanding today with a spinning neutron star, a pulsar, at its heart, blinking like a cosmic lighthouse 30 times per second. The explosion itself happened 6,500 years before those medieval astronomers saw it. The light was already ancient when it arrived. But a supernova, as extraordinary as it is not what we're here to talk about tonight. Because a supernova is not the most powerful explosion in the universe, not even close. For that, we need to follow what happens when the collapse of a massive star's core doesn't produce a neutron star, but instead goes further. When gravity wins so completely, so absolutely, that even neutron degeneracy pressure, the quantum mechanical force that holds neutron stars together, cannot resist the crush. When everything collapses into a singularity, when a black hole is born. A black hole is one of the strangest, most fascinating and most philosophically vertiginous objects in all of physics. It forms when matter is compressed so completely that all of it, every atom, every neutron, every quantum of material, is squeezed down into a single point of infinite density, a singularity. Around that point, the gravitational field is so intense that it warps the fabric of space-time itself, not just pulling on matter, but bending space and slowing time in a way that becomes more and more extreme as you approach the center. At a certain distance from the singularity, a distance that depends on the mass of the black hole, the escape velocity required to break free of the gravitational pull reaches the speed of light. And since the speed of light is the absolute cosmic speed limit, since nothing in the universe can travel faster, nothing inside that boundary can ever escape. Not matter, not energy, not information, not light. That boundary is called the event horizon. It is not a physical surface. There's no wall there, no barrier you could see or touch. It is simply the point of no return. The boundary between the region where escape is possible and the region where it is not. And once you cross it, the laws of physics as we understand them break down. Time behaves in extraordinary ways near a black hole. If you were to hover just outside the event horizon, time would pass more slowly for you than for someone far away. Dramatically, measurably, profoundly, more slowly. A clock on the surface of a neutron star ticks slightly more slowly than a clock far out in space because of its gravitational field. Near a black hole, this effect becomes extreme. Near the event horizon, time nearly stops from the perspective of a distant observer. If you were watching a friend fall toward a black hole from a safe distance, you would see them slow as they approached the horizon. Their image would grow redder. The light they reflected stretched to longer wavelengths by the intense gravity. They would appear to freeze in place at the horizon, suspended, like a film paused on the last frame. Their clock, seen from your vantage point, would stop. But from their own perspective, they would pass through the event horizon in moments, feeling nothing unusual as they crossed it. The universe curves around a black hole so strangely that the inside and outside experience something fundamentally different. Observer-dependent, relative, paradoxical. This is the nature of space-time near the most extreme objects in the cosmos. Black holes come in several sizes. Those formed by the collapse of individual massive stars are called stellar mass black holes, typically between a few times and perhaps 100 times the mass of our Sun, compressed into a region of space just a few kilometers across. And then there are the supermassive black holes that sit at the centers of most large galaxies. These are monsters, containing millions, hundreds of millions, even billions of solar masses, compressed into a region perhaps the size of a solar system. Our own Milky Way hosts a supermassive black hole at its center called Sagittarius, a star, containing about 4 million solar masses. The black hole at the center of the galaxy M87 made famous by the first direct image of a black hole's shadow captured in 2019 by the Event Horizon Telescope, contains 6.5 billion solar masses, a black hole more than 1,000 times more massive than the one at the center of our own galaxy. A truly incomprehensible concentration of matter in a single point. For most of their existence, black holes are quiet and dark. They sit in the black, invisible, detectable only by the gravitational pull they exert on surrounding stars and gas, or by the bending of light from objects behind them. They don't glow on their own. They don't roar or pulse. They simply exist, patient and dense and dark, like stones at the bottom of a very deep river, invisible from the surface, but always there, felt in the slow and subtle pull of the current. But sometimes a black hole is not quiet. Sometimes matter falls toward it, gas drifting in from nearby space, or the outer material of a companion star being stripped away by gravity, or sometimes an entire star that has wandered too close and is torn apart by tidal forces into a long stream of debris that spirals inward. As this material falls toward the black hole, it can't fall straight in. It has angular momentum, a spin, and so instead it forms a flattened, rotating disk around the black hole, called an accretion disk. As matter spirals inward through this disk, it moves faster and faster and heats up to extraordinary temperatures, millions of degrees, sometimes tens of millions of degrees. The disk glows. In fact, it glows brilliantly. An accretion disk around an active black hole can outshine an entire galaxy. These are the objects we call quasars, quasi-stellar objects, the brightest things in the universe, powered by matter falling into a supermassive black hole at the center of a distant galaxy. Along with the radiation from the accretion disk, powerful magnetic fields build up in the turbulent, spiraling plasma. And along the poles of the black hole, along the axis around which it spins, these magnetic fields can focus and concentrate the outflowing energy into narrow, focused jets of plasma and radiation, firing outward at nearly the speed of light. These jets can extend for thousands of light years. They can punch holes in the surrounding gas of the galaxy. They are among the most energetic ongoing phenomena in the known universe. And when the conditions are just right, when a very massive star collapses directly into a black hole, or when two neutron stars merge after spiraling together for billions of years, those jets become something even more extreme. For a brief and terrible interval, they release more energy than almost anything else in the cosmos. They become the source of a gamma-ray burst. Gamma rays are a form of electromagnetic radiation, part of the same broad family as visible light, radio waves, infrared light, ultraviolet light, and X-rays. All of these are fundamentally the same type of wave, oscillating electric and magnetic fields propagating through space at the speed of light, differing only in their frequency and wavelength. Think of the electromagnetic spectrum as a vast keyboard stretching from one end of the horizon to the other. Radio waves are the deep, resonant bass notes at one end. Long, slow waves, low in energy, the kind that carry your favorite radio station into your car's speakers. Microwaves sit just above them, the waves that heat your food. Infrared light comes next, carrying the warmth of the sun on a summer day. Then visible light, the narrow band of wavelengths that our eyes evolved to detect, from red through orange, yellow, green, blue, and violet. Then ultraviolet, which causes sunburn. Then X-rays, which pass through soft tissue but are absorbed by bone. And at the very far end of the keyboard, where the notes are so high and so fast they are utterly beyond anything we can feel or see or hear, are gamma rays, the most energetic photons in existence. Individual gamma-ray photons carry more energy than photons of any other type of electromagnetic radiation. A single gamma-ray photon can carry millions of times more energy than a photon of visible light. When a gamma-ray burst fires, it releases an almost inconceivable number of these extreme energy photons, focused into a narrow beam and aimed outward across the universe. The beam is tight, covering only a small angle of the sky, like a focused spotlight rather than a bare light bulb. If you were in the path of that beam, even from across the galaxy, the experience would be brief and final. But for those of us not in the path, for observers at safe distances and angles, a gamma-ray burst is a brief, brilliant flash of the highest energy light the universe produces. A cosmic lighthouse sweeping its beam across the dark. Gamma-ray bursts were first detected entirely by accident. In the late 1960s, the United States Air Force launched a series of satellites called Vela, designed not to study astronomy, but to monitor for nuclear weapons tests in space. The Cold War was at its tense and anxious height, and there were genuine concerns that a nuclear power might detonate a weapon in orbit in violation of the 1963 Partial Nuclear Test Ban Treaty. The Vela satellites were equipped with detectors sensitive to the gamma radiation that a nuclear explosion produces. They were watching the sky for humanity's own violence. What they found, instead, was the universe's. Beginning in 1967, the Vela satellites began detecting brief, intense bursts of gamma radiation arriving from random points across the sky. The signals came and went in seconds. They were brighter, far brighter, than any gamma radiation that could be produced by a nuclear weapon. And they came from all directions equally, with no preference for the plane of the Earth's orbit or the plane of the Milky Way. The analysts who first examined the data were baffled. They couldn't explain it. The information was classified for several years while the military tried to determine what it was seeing. Finally, in 1973, the existence of gamma-ray bursts was declassified and reported in scientific journals. The astronomical community, which had not known these phenomena existed, was immediately fascinated. For decades afterward, gamma-ray bursts remained one of the greatest open mysteries in astrophysics. New bursts were detected regularly, but they faded so quickly, leaving so little trace that follow-up observations were nearly impossible. Every burst came from a different part of the sky. Were they near, and therefore merely moderately powerful? Or were they at cosmological distances, billions of light years away, which would make them almost unimaginably energetic? Astronomers debated fiercely. The answer had enormous implications for physics and cosmology. The breakthrough came in 1997. A burst called GR B970508 was detected, and for the first time, astronomers managed to catch its afterglow, a slowly fading glow of X-ray and visible light that lingered for days after the initial burst. By measuring the spectrum of that afterglow, they were able to detect the characteristic absorption lines of intervening matter, and to measure the redshift, the stretching of the light's wavelengths due to the expansion of the universe. The measured redshift confirmed that the burst was at a distance of at least 6 billion light-years. The debate was over. Gamma-ray bursts were cosmological. They came from across the universe, and that meant they were releasing energy on a scale that redefines the word powerful. We now know that gamma-ray bursts come in two main varieties, divided by their duration. Short gamma-ray bursts last less than 2 seconds, often far less, sometimes just a few milliseconds. They are thought to originate from the collision of two extremely dense stellar remnants, two neutron stars, or a neutron star and a black hole, that have been spiraling toward each other for billions of years, losing energy to gravitational radiation until they finally merge in a cataclysmic instant. In 2017, astronomers detected both the gravitational waves and the gamma-ray burst from such a merger event, for the first time confirming the connection and opening a new era of multi-messenger astronomy. Long gamma-ray bursts, which last more than 2 seconds, sometimes minutes, are thought to be produced by the collapse of the core of a very massive star directly into a black hole, in an event sometimes called a collapsar or hypernova. The collapse happens. The black hole forms. Jets of plasma and radiation fire outward through the remaining stellar material at nearly the speed of light, drilling through the star and emerging from the poles. The surrounding star, or what's left of it, explodes in a supernova that may be 10 or 100 times more energetic than a typical stellar explosion. In both cases, the merger and the collapsar, what drives the gamma-ray burst is the same. A newborn black hole spinning rapidly, feeding on nearby material, channeling energy into those narrow, focused, devastating jets. The black hole is the engine. The jet is the beam. And the beam sweeps out across the universe, carrying the news of a cosmic catastrophe at the speed of light. Now, let's talk about the most powerful one ever recorded. To do that, we need to travel to the 9th of October, 2022. It was an ordinary autumn morning on Earth, or rather, it was ordinary in the way that all mornings feel ordinary until something changes them. In the northern hemisphere, leaves were turning gold and amber on the trees. Somewhere, children were eating breakfast. Coffee was being poured. Somewhere else, people were just going to sleep as the sun came up. The planet was turning in its unhurried way, carrying its billions of small lives through their daily rhythms, while in the sky above, invisible to all but the machines we had built to watch, the cosmos was doing what it always does, turning, burning, evolving, sending us its light. At 13 hours, 21 minutes, and 59 seconds coordinated universal time, something extraordinary arrived. A wave of gamma radiation swept across the Earth. It had been traveling for approximately 1.9 billion years. When this explosion occurred, when this beam of energy was first fired outward across the cosmos, multicellular life on Earth had barely begun. The first simple animals were only just starting to appear in the Precambrian oceans. There were no fish yet, no insects, no plants on land, no dinosaurs, no mammals, no humans. The continents were shaped completely differently. For 1.9 billion years, while life on Earth slowly evolved through all its magnificent complexity, from single cells to ferns to forests to dinosaurs to us, this wave of radiation had been crossing empty space at the speed of light in a perfectly straight line, heading for where our solar system would one day be. And on October 9th, 2022, it arrived. The burst was detected simultaneously by multiple spacecraft. NASA's Fermi Gamma Ray Space Telescope, a dedicated observatory in Earth orbit specifically designed to watch for these events, registered the signal. So did NASA's Swift satellite. So did other instruments, both in space and on the ground. Within seconds, automated systems generated alerts and transmitted them to observatories around the world. Telescopes slewed on their mounts, repointing to the source. The global network of astronomers coordinated rapidly, each observatory taking observations in its own wavelength band. Gamma rays, X-rays, ultraviolet, visible light, infrared, radio. Within hours, a detailed picture was beginning to emerge. The burst was formally designated GRB2210009A, following the standard naming convention for gamma ray bursts, the year, month, and day of detection, followed by the order of detection that day. But the designation felt inadequate almost immediately. Astronomers started calling it the boat, the brightest of all time. The name was not an exaggeration. In terms of the gamma ray flux received at Earth, the intensity of the radiation detected by our instruments, GRB2210009A, was not merely the most powerful gamma ray burst ever recorded. It was more powerful than anything previously recorded by an enormous margin. Some estimates placed it as a 1 in 10,000 year event, an explosion of this magnitude occurring in the detectable universe perhaps once in 10 millennia. Others suggested it might be even rarer than that. Some of the gamma ray detectors aboard the Fermi satellite saturated entirely during the peak of the burst. They registered the maximum signal their electronics could handle, and the true peak intensity could only be reconstructed through careful mathematical analysis afterward, like trying to read a page that had been so bright it burned the eye. The burst lasted several hours in total, an extraordinary duration. Most gamma ray bursts are over in seconds or minutes. The fact that GRB2210009A's emission continued to be detectable for hours spoke to the extraordinary energy involved and to the unusual conditions of the event. The most intense phase of gamma ray emission lasted for several hundred seconds, a few minutes. But the afterglow lingered in X-rays and radio waves and visible light for months. Observatories around the world and in space continued to watch it, cataloguing its slow fade, measuring its spectrum, extracting every scrap of information the dying signal could offer. The estimated total energy released was somewhere around 10 to the power of 54 joules, possibly more. Writing that out in full, 1 quintillion joules. Or, to make the comparison, that 1 quintillion joules is approximately equal to 1 quintillion joules. Or, to make the comparison that matters most, the Sun, burning hydrogen at its core for 10 billion years, will emit roughly 10 to the power of 44 joules over its entire lifetime. GRB2210009A, released in a few minutes of jet activity, approximately 10 billion times more energy than the Sun will produce in its entire existence. 10 billion Sun lifetimes of energy, focused into a narrow beam, fired across the cosmos in the time it takes to boil a kettle. The ionosphere of Earth, the upper layer of the atmosphere, where the air is thin and electric, where the aurora dances, was measurably disturbed by the burst. Scientists detected an anomalous ionospheric disturbance coinciding precisely with the arrival of the gamma radiation. From 1.9 billion light-years away, the explosion was still powerful enough to leave a fingerprint in the atmosphere of a small planet orbiting an unexceptional star on the outskirts of an average galaxy. We didn't feel it. We couldn't feel it. But our instruments noticed. The sky hiccuped almost imperceptibly, and our machines were sensitive enough to catch the hiccup. The event that produced GRB 221009A was almost certainly the collapse of a very massive star, perhaps 30 or 40 times the mass of our Sun, into a rapidly spinning black hole. In the final fraction of a second of that star's existence, its iron core, the accumulated ash of billions of years of nuclear burning, could no longer support its own weight against gravity. It collapsed. In less than half a second, the core went from something the size of the Earth to something the size of a city. The outer layers of the star, crashing inward at a significant fraction of the speed of light, rebounded off the newly formed compact remnant and were expelled outward in a hypernova explosion. But before the explosion had finished clearing the stellar material away, the most extraordinary part of the event had already begun. The newly formed black hole, spinning rapidly, surrounded by a dense torus of hot material, had fired its jets. Those jets punched through the collapsing stellar envelope like needles through cloth. They emerged from the poles of the dying star, carrying concentrated beams of energy at 99.9% of the speed of light. One of those jets happened to be aimed in our direction, and 1.9 billion years later, it reached us. The star that produced GRB 221009A no longer exists. It hasn't existed for 1.9 billion years. The galaxy in which it lived, a faint, ordinary smudge of starlight catalogued in our survey databases, continues its slow rotation, indifferent to the catastrophe that happened in one corner of it so long ago. The black hole that formed in the collapse is there, somewhere, cooling and dark, perhaps accreting some small amount of surrounding material, perhaps completely quiet now. Everything about that event is ancient history. The drama played out and concluded before the first fish swam in Earth's oceans. But the light remembers. The light always remembers. It carries the record of events across the universe, encoded in its wavelengths and its timing, perfectly preserved for however long it takes to arrive at something capable of detecting it. And on that October morning in 2022, it arrived at us. There is something deeply moving about this if you let yourself feel it, here in the quiet dark of wherever you're resting. The universe is so vast and so old that everything we observe is, in a sense, archaeology. When you look at the night sky, you are not seeing the stars as they are right now. You are seeing them as they were, years, decades, centuries, sometimes millennia ago. The light from Sirius, the brightest star in the night sky, takes about 8.6 years to reach us. The light from the brightest star in Orion's belt takes about 800 years. What you see tonight left that star around the time of the Crusades. The light from the Andromeda Galaxy, the nearest large galaxy to our own, takes 2.5 million years. It left when our ancestors were making the first stone tools. And the light from a gamma-ray burst detected this year left its source when Earth was still the domain of primitive marine organisms. We are surrounded by ancient light. The night sky is a time machine. Every direction you look is a window into the past. The deeper into space you look, the further back in time you see. And at the very edge of what our instruments can detect, at redshifts of 10 or more. We are seeing the universe as it was just a few 100 million years after the Big Bang. The universe in its infancy. Stars and galaxies forming for the first time. A cosmos that looks almost nothing like the one we inhabit today. The James Webb Space Telescope, launched in late 2021 and fully operational by 2022, the same year GRB 221009A occurred, has become the most powerful window into this ancient light ever constructed. With its enormous mirror, cooled to temperatures colder than the deep of space, sensitive to the infrared light that ancient red-shifted galaxies emit, the Webb telescope has peered into the universe's earliest eons with unprecedented clarity. It has found galaxies that formed startlingly early, earlier than many models predicted, massive and bright and complex, glowing in the infrared from across 13 billion years of cosmic time. Each image from Webb is a reminder that the universe has been creating complexity and beauty for far longer than we instinctively imagine. Let's float away from the drama of explosions for a while now and drift into something quieter. Let's talk about the texture of space itself, about what fills the vast distances between things. Space is not empty. This is one of the most consistently surprising facts about the cosmos, for people who haven't encountered it before. We tend to picture space as a pure and featureless void, the black background of a planetarium's ceiling, punctuated by the distant pinpricks of stars. But space is filled with things, thin things, subtle things, things that reveal themselves only to patient observation and sensitive instruments. But things nonetheless. Between the stars in the disk of a spiral galaxy like ours, there is the interstellar medium, a tenuous mixture of gas and dust threading its way through the entire galaxy. The gas is mostly hydrogen in various forms, sometimes in the form of individual atoms floating freely in the near vacuum of interstellar space, sometimes in the form of ions stripped of their electrons by the ultraviolet radiation of nearby hot stars, sometimes in cold and dense molecular clouds where hydrogen atoms bind together in pairs, and more complex molecules, including organic molecules, the building blocks of chemistry, form on the surfaces of tiny dust grains. The dust itself is made of silicate minerals and carbon compounds, tiny grains, each smaller than a bacterium, drifting through space, absorbing and scattering light, blocking our view of distant regions behind them, slowly building up in cold, dense clouds until gravity gathers them into new stars and planets. Some of these clouds are illuminated by nearby stars and glow with colors so beautiful they seem painted. These are emission nebulae, regions where the gas has been energized by the ultraviolet radiation of hot young stars, absorbing that energy and re-emitting it as visible light of characteristic wavelengths. Hydrogen emits a deep, warm red. Doubly ionized oxygen emits a blue-green. Singly ionized sulfur emits red and orange. When we combine these emission lines in false color images, mapping each element's glow to a different visible color, the result is the palette of some of the most iconic astronomical images ever made. The pillars of creation, the Carina Nebula, the Orion Nebula, vast, luminous, cloud-sculpted structures glowing with the light of the elements, shaped by the stellar winds and radiation of the massive young stars being born within them. Other nebulae are the remnants of stellar deaths, supernova remnants, expanding shells of ejected stellar material, glowing as the shockwave heats the surrounding interstellar gas. the Crab Nebula, Cassiopeia A, the Veil Nebula. Each of these is a scar left in the interstellar medium by the explosion of a massive star, slowly expanding over thousands of years, still warm and glowing, still pushing outward against the surrounding space. Some of them are still producing new shockwaves as the central remnant, a neutron star spinning and pulsing, continues to pump energy into the surrounding nebula. And between the galaxies, in the vast expanses of intergalactic space, there is yet more material. The intergalactic medium is even more diffuse than the interstellar medium. Hot, ionized gas that fills the spaces between galaxies, heated by the same ultraviolet radiation that keeps hydrogen ions stripped of their electrons in the early universe. It is so thin that it is effectively transparent to most wavelengths of light. But it is there, in enormous quantities, filling the filaments and sheets of the cosmic web. The cosmic web is the name we give to the large-scale structure of the universe, visible only when you zoom out to scales of hundreds of millions or billions of light years. On these scales, galaxies are not randomly distributed. They cluster together along filaments, long, thin threads of matter that intersect at dense nodes where the largest galaxy clusters accumulate. Between the filaments are vast empty regions called voids, spherical or elliptical expanses of space, hundreds of millions of light years across, where galaxies are extraordinarily rare. The pattern resembles foam, or soap bubbles, or the inside of a sponge, or the web of a spider, or perhaps most evocatively, the pattern of neurons in a brain, with filaments connecting nodes and vast spaces in between. The cosmic web is shaped primarily by dark matter, a mysterious substance that makes up about 27% of the total energy content of the universe, compared to just 5% for ordinary visible matter. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. It reveals itself only through gravity, by the way its mass bends light from objects behind it, a phenomenon called gravitational lensing, and by the way it affects the rotation of galaxies and the formation of large-scale structure. We can map the dark matter distribution indirectly by observing these gravitational effects. And what we find is that ordinary matter, stars, gas, dust, galaxies, traces the scaffolding of dark matter, clustering along the same filaments and nodes that dark matter defines. And then there is dark energy, an even more mysterious component, making up about 68% of the universe's total energy content. Dark energy is what we call the cause of the universe's accelerating expansion. In 1998, two independent teams of astronomers made the remarkable discovery that the universe is not merely expanding, it is expanding faster and faster over time. The most distant supernova they were observing were fainter than expected, meaning they were further away than expected, meaning the expansion of the universe had been accelerating since they exploded. Something was pushing the universe apart, counteracting gravity on the largest scales. We call it dark energy. We don't know what it is. It may be an intrinsic energy of empty space, the vacuum itself possessing a kind of built-in pressure that pushes outward. It may be something else entirely. It is one of the deepest unsolved problems in physics. Think about what this means. 95% of the universe is made of things we cannot see, cannot directly detect, and do not fundamentally understand. The ordinary matter, The atoms, the molecules, the stars and planets and people makes up just 5% of what exists. The universe is mostly dark in ways we are only beginning to map. And yet, that 5% has produced extraordinary complexity. Stars and galaxies and nebulae, planets with oceans, life, consciousness, telescopes that can detect gamma-ray bursts from across the observable universe. The universe's visible matter, though a small fraction of the whole, has organized itself into structures of staggering beauty and variety. What the dark components are doing, what complexity, if any, they harbor, we cannot yet say. Let's come closer again. Let's come home to our own galaxy and take a slow, meditative tour of the neighborhood. The Milky Way is a barred spiral galaxy, a flat disk of stars, gas, and dust, about 100,000 light-years across, and roughly 1,000 light-years thick in the plane of the disk. Looking at it from outside would reveal a bright central bar surrounded by a bulge of older stars, from which two main spiral arms, the Perseus arm and the Scutum Centaurus arm, extend outward with smaller arms and spurs branching off from them. The entire disk is embedded in a more diffuse halo of older stars. The population 2 stars, ancient and metal-poor, orbiting the galactic center in long elliptical paths that carry them far above and below the plane. And surrounding everything, extending for hundreds of thousands of light-years, is the dark matter halo, the invisible scaffolding that holds the galaxy together and gives it its shape. Our solar system is located about 26,000 light-years from the galactic center in a modest spur called the Orion Arm, a minor spiral feature branching off from one of the main arms. It's a relatively quiet suburb of the galaxy, not too close to the crowded, turbulent center, not too far out in the sparse outer reaches. The kind of galactic neighborhood where a star can burn steadily for billions of years without too many catastrophic disruptions. This relative quiet may not be coincidental. The stability of our solar system over billions of years, which allowed complex life to evolve, may be partly a consequence of our fortunate address. The Sun orbits the galactic center at a speed of roughly 230 kilometers per second, fast enough to circle the Earth in under 3 minutes, and takes about 225 million years to complete one orbit. This cosmic year, as it's sometimes called, is a useful unit for thinking about geological and biological timescales. The age of the Earth is about 20 galactic years. The dinosaurs went extinct less than 1 galactic year ago. Modern humans have existed for less than 1,000th of a galactic year. Looking toward the center of the galaxy from Earth, we look in the direction of the constellation Sagittarius. And it is in that direction, buried behind dense clouds of gas and dust that block visible light, that Sagittarius A star lies. We cannot see it optically, but we can observe it in radio waves and infrared light and X-rays, which penetrate the dust more easily. Over decades of observation, astronomers have tracked the motions of stars in the very center of the galaxy. Stars moving at extraordinary speeds, some completing full orbits around the central point in only a few years. And from these orbits, using Kepler's laws and Newton's mathematics, they have calculated the mass of whatever lies at the center. The answer is unambiguous: 4 million solar masses, concentrated in a region far smaller than our solar system. Only a black hole fits. Only a black hole of that mass in that space is consistent with what we observe. In 2022, the same year as the boat, the Event Horizon Telescope collaboration published the first image of Sagittarius A star. Not an artist's impression, an actual image assembled from radio observations taken simultaneously at radio telescopes distributed across the Earth, forming an effective telescope dish the size of the planet. The image showed what all the models predicted: a ring of bright, hot, glowing material surrounding a central dark shadow, the silhouette of the event horizon against the glow of the accretion disk. The shadow of a black hole at the center of our own galaxy, seen for the first time with human-made instruments. A dark circle, a few tens of millions of kilometers across, from 26,000 light-years away. It was a moment of quiet wonder for those who understood what they were looking at. That dark circle, that absence, that hole in the light, is the mark of an object so dense and so gravitationally extreme that even light cannot escape. And it sits at the heart of the galaxy we call home. We orbit it. Every star in the Milky Way orbits it. We have always orbited it, since before the Earth formed, and we will continue to orbit it long after the Sun has burned out. The black hole was there before us. It will be there after us. It is as much a part of our address as the galaxy itself. Now let's talk about time. Because time in the universe's story is not the simple linear river we experience from the inside. It is something stranger, more flexible, and in a way more beautiful than our everyday experience suggests. Einstein's theories of relativity, special relativity published in 1905 and general relativity published in 1915, rewrote our understanding of space and time more profoundly than anything since Newton. Before Einstein, time was assumed to be universal, a fixed, absolute backdrop against which events happened, ticking along at the same rate for everyone, everywhere, regardless of their motion or location. Newton's clockwork universe ran on a universal clock, and that seemed obvious and natural and beyond question. Einstein showed that it was wrong. In special relativity, the rate at which time passes depends on your speed. The faster you move relative to another observer, the more slowly your clock ticks from their perspective. This is not a technological limitation or an illusion. It is a fundamental feature of the geometry of space-time. The faster you move through space, the slower you move through time. The relationship is precise and mathematical, described by the Lorentz factor. At everyday speeds, even the speed of a jet airplane or a satellite in orbit, the effect is tiny, measurable only with extremely precise atomic clocks. But it is real. It has been confirmed repeatedly by experiment. At speeds approaching the speed of light, the effect becomes dramatic. At 90% of the speed of light, time for a moving observer ticks at roughly 44% of the rate it does for a stationary observer. At 99% of the speed of light, the ratio drops to about 14%. At 99.9%, it's about 4.5%. The closer you get to the speed of light, the slower your time flows relative to the outside world. And at the exact speed of light, which is only achievable by massless particles like photons, time stops entirely. A photon, from its own reference frame, if it had one, experiences zero time between emission and absorption. It is born and dies in the same instant. The 1.9 billion years that the boat's gamma-ray photons spent crossing space were not experienced by those photons at all. They traversed the universe in no time at all from their own perspective. General relativity extended these ideas to include gravity. Gravity, Einstein proposed, is not a force in the Newtonian sense, a mysterious action at a distance pulling masses toward each other. It is the curvature of space-time caused by the presence of mass and energy. Massive objects bend space-time around them, the way a heavy ball placed on a stretched rubber sheet creates a depression that other objects roll toward. And this curvature affects not just the paths of moving objects, but the flow of time itself. Deep in a gravitational well, close to a massive object, time flows more slowly than far away. This gravitational time dilation has been confirmed with extraordinary precision. Clocks at lower altitudes, where Earth's gravity is slightly stronger, tick slightly more slowly than clocks at higher altitudes. The GPS satellites in orbit must account for this effect, along with the opposing effect from their high speed, as predicted by special relativity. Or their position calculations would drift by kilometers per day, making GPS useless for navigation. Every time you use a map on your phone and it places you correctly on a street, you are benefiting from Einstein's understanding of how gravity bends time. Near extreme gravitational objects, neutron stars, and especially black holes, these effects become profound. A clock hovering just outside the event horizon of a black hole would appear, from a distance, to be ticking infinitely slowly. Time at the edge of a black hole is stretched almost to a standstill relative to the rest of the universe. If somehow you could hover at that edge for what felt to you like an hour, and then escape back to the outside, you might find that the universe had aged by billions of years in your absence. The universe flows fast, out there in the open. Time is most generous with those who stay far from the heavy things. And there is one more twist to time that is worth lying with in the quiet of tonight. Time, in the equations of physics, is not fundamentally different from the three dimensions of space. It is the fourth dimension of a four-dimensional space-time. The past, present, and future are all, in some sense, equally real, laid out along the time axis the way different locations are laid out along the spatial axis. What we experience as the flow of time, the sense of moving from past to present to future, the arrow of time, is not a feature built into the fundamental laws of physics, which are mostly time-symmetric. It emerges, physicists believe, from the direction of increasing entropy, the tendency of systems to move from ordered to disordered states. Time flows forward because the universe began in an extraordinarily ordered state, and disorder has been increasing ever since. The universe began with very low entropy. The Big Bang, hot and dense and smooth, was a state of enormous order, or rather thermal order. Everything compressed together. And since then, entropy has been increasing. Structure has formed, stars and galaxies, but only because gravity has been concentrating matter and creating energy differentials that drive chemical and physical complexity. And eventually, in the very long future, after all the stars have faded, after all the black holes have evaporated, entropy will reach its maximum. The universe will be uniformly cold and dark and featureless at thermal equilibrium. The arrow of time will have nowhere left to point. Things will simply be without changing. The universe's long exhale finally complete. But that end is inconceivably far away. And between here and there lies an almost infinite expanse of time during which stars will burn, galaxies will collide and reform. Life may arise on worlds we'll never see, and whoever or whatever inherits the universe will look up at whatever sky they have and wonder, just as we do. We are such a small part of this story, and yet we are the part of it that is awake right now, looking up, listening. The part that built the telescopes and launched the satellites and detected the boat on an autumn morning in 2022. The part that felt something, call it wonder, call it humility, call it awe, when the numbers came back and the scale of the event became clear. We are matter that has become aware of the universe's own explosions. That is an extraordinary thing to be. Your body, resting there in the dark, is made of atoms forged in stars. Your iron, your calcium, your carbon, all of it produced in nuclear furnaces and scattered through space in explosions far older than the Earth. The calcium in your bones was made in a supernova. The iron in your blood was made in the core of a star that ran out of fuel and exploded, perhaps 5 or 6 billion years ago, seeding the cloud of gas that would eventually become our solar system. You are not separate from the universe. You are a temporary and elaborate arrangement of the universe, looking at itself. When the boat's gamma radiation washed over Earth on that October morning, it passed through everything, through the atmosphere, through the ionosphere, through the bodies of everyone alive on the surface of the planet. Those gamma-ray photons, having traveled 1.9 billion years from the site of a cosmic catastrophe, passed through you, through your skin and your blood and your bones and your sleeping brain. You didn't feel it. There was no sensation. But for a fraction of a second, you were touched by something that had been traveling since before the first animals evolved on Earth. Something ancient. Something that carries, encoded in its wavelength and its timing, the story of a star dying in another galaxy 1 billion years before your world existed. The universe is always touching you. It flows through you in neutrinos, billions every second, passing through the entire Earth without stopping, from the nuclear reactions in the Sun and from supernovae in distant galaxies. It holds you with gravity. It warms you with sunlight that is 8 minutes old. It shows you ancient light every time you look at the stars. The universe is not distant and remote, something you observe from outside. You are inside it. You are woven into it. It acts on you and through you every moment of every day and every night. Let that settle for a moment as your breath slows and your body grows heavier and warmer. You are not alone out here. You are held, quietly and without effort, by the same forces that hold galaxies together. Gravity is cradling you right now, pressing you softly and persistently into your bed, keeping you anchored to this small blue spinning world. The same gravity that pulls gas clouds into stars, that holds solar systems in their shapes, that bends light around black holes and sculpts the cosmic web. That same force is holding you gently right now. It has been holding you every moment of your life, and it will hold you through the night. Let it hold you. Our own galaxy, the Milky Way, is drifting through space as well. Not randomly, but pulled by gravity toward a vast concentration of mass, about 250 million light-years away, a region astronomers call the Great Attractor. Hundreds of galaxies, including our own, are flowing toward it at hundreds of kilometers per second. And yet, we don't feel this motion at all. It is silent. It is smooth. The universe moves in ways too large and too slow for our senses to register, and we are carried along inside it like motes of dust drifting in an imperceptibly slow current of air. There are about 2 trillion galaxies in the observable universe. 2 trillion. Each one containing hundreds of billions of stars, each star potentially surrounded by planets. The numbers are so large they lose meaning if you try to hold them directly. They slide through the mind like water through opened fingers. But try to feel them instead of count them. Try to sense the sheer density of the universe's creativity. 2 trillion islands of light, each one its own vast system of suns and worlds, scattered across a sphere 93 billion light-years wide. And beyond the edge of that observable sphere, beyond the distance light has had time to travel since the Big Bang, the universe continues, perhaps forever. We can't see past that horizon. But the physics suggests that what lies beyond it is more of the same. More galaxies, more stars, more worlds, stretching outward in all directions without bound. The universe may be infinite, not very large, not almost infinite, truly, literally infinite, extending without end in every direction, filled with matter and energy and structure all the way to forever. If so, then everything that can happen does happen. Somewhere. Every possible configuration of matter, every possible world exists somewhere in the infinite expanse. There are other stars like our Sun, other planets like our Earth, other beings resting in the dark, listening to the quiet, wondering about the universe. We cannot reach them, we cannot communicate with them. But the mathematics of infinity suggests they exist. Or perhaps the universe is finite, curved back on itself, like the surface of a sphere, so that if you traveled far enough in one direction, you would eventually return to where you started. We don't know. Our instruments can only see so far. The universe's true geometry, whether it is flat, positively curved, or negatively curved, whether it is finite or infinite, is still a question that physics cannot yet definitively answer. We know only that it is very, very large, and that it has been expanding for a very, very long time, and that it contains more wonder than any mind can fully hold. And at the heart of all of this, at the center of all the complexity and violence and beauty, is a simplicity that is almost miraculous. A handful of fundamental forces, a small set of elementary particles, a few basic laws of physics. From these ingredients, from gravity and electromagnetism and the nuclear forces, from quarks and electrons and photons, from quantum mechanics and general relativity, the universe assembled everything. Every star, every planet, every ocean and mountain, every bacterium and flower and human being, every thought and dream and memory, all of it emergent from a few lines of cosmic law, written in the first moments after the Big Bang and unchanged since. That simplicity underlying the complexity is one of the things that scientists find most beautiful about the universe. Not just that it is vast and ancient and full of extraordinary events, but that it is comprehensible. That we, brief and fragile creatures on a small planet, have managed to read some of the laws. That mathematics, invented by human minds to describe abstract relationships, turns out to also describe the behavior of stars and black holes and the large-scale structure of the cosmos. That the universe is, in some deep sense, rational, understandable, open to inquiry. There is a phrase sometimes attributed to the physicist Eugene Wigner about the unreasonable effectiveness of mathematics in the natural sciences. Why should the equations we write on whiteboards accurately predict the behavior of objects billions of light years away that no human has ever observed? There's no obvious reason why this should be so, and yet it is. The same mathematics that describes the orbit of a pendulum describes the orbit of a planet. The equations of electromagnetism derived from experiments on Earth correctly predict the emission spectra of stars on the other side of the universe. The physics of nuclear fusion, developed in laboratories, correctly describes what happens in the core of a star we can never visit. The universe behaves as if it were written in the language of mathematics, and we have been slowly learning to read it. You are one of the universe's readers. Every human who has ever learned to count, or noticed a pattern in the seasons, or looked at the sky and wondered, every person who has felt curiosity and followed it, has been participating in this ancient project of reading the universe's language. You don't need to be a physicist or an astronomer to participate. You only need to wonder. And you are doing that right now, aren't you? Even as your eyes grow heavy and your thoughts begin to soften at the edges. Even now, you are in relationship with the cosmos, listening to it, letting it speak. The gamma-ray burst we've been talking about, the boat GRB 221009A, has already told us things we didn't know before. Astronomers studying its afterglow have found evidence for the formation of heavy elements, specifically elements heavier than iron, created in the extraordinarily energetic conditions of the explosion itself. The process that creates these heavy elements is called the R process, rapid neutron capture, and it can only happen in environments of extreme neutron density and energy. Neutron star mergers and hypernovae are thought to be its primary sites in the universe. Gold, platinum, uranium, iodine, which your thyroid needs to function. These elements, too rare to be formed in ordinary stellar nucleosynthesis, are born in the universe's most violent moments and scattered across space in their explosions. The gold in any ring or necklace you might own, the gold in any device, any coin, any ancient treasure, was born in a cosmic catastrophe, in a neutron star merger or a hypernova, or an event very much like the boat. It was forged in an instant of unimaginable violence, flung across space, gathered into a cloud, incorporated into a solar system, deposited on a planet, found by a living creature, and shaped into something beautiful. Violence transformed, over billions of years, into ornament, into meaning, into a wedding band placed on a finger, a necklace passed from grandmother to grandchild, a crown resting in a museum case. The universe's most extreme explosions distilled into objects of human significance. There is a poetry in that which no one planned or intended. The universe doesn't have intentions. It simply has laws. And the laws, applied over billions of years, produce outcomes that feel like poetry, feel like meaning, to the conscious beings who find themselves embedded in the result. The night is quieter now, isn't it? Whatever sounds surrounded you earlier have softened. The world outside has settled. Your own breathing has slowed, deepened, grown more regular without any effort on your part. Your body knows how to do this. It has known for as long as you have been alive. This slow, patient surrender to sleep, this nightly letting go. Every night of your life, without exception, you have released your grip on wakefulness and allowed yourself to drift. And every morning, you have returned. Sleep is the most trusting thing we do. It is a daily act of faith in the continuity of the world. The universe around you will continue while you sleep. The stars will not pause. The galaxies will continue their slow rotation. Somewhere, right now, a star is being born in a collapsing cloud of gas, a process that began millions of years ago and will continue for millions more, happening so slowly that nothing in a human lifetime could observe its progress, and yet happening nonetheless, silently and surely, in the dark between the stars. Somewhere else, a star is dying, running out of fuel, expanding into a red giant, beginning the long process of shedding its outer layers. And somewhere, in a galaxy we have perhaps not yet catalogued and named, a massive star is in the last hours of its life. Its iron core is accumulating, growing heavier and heavier. The nuclear burning in its outer shells continues for now, but the end is close. Soon, perhaps tonight, perhaps in 1,000 years, perhaps in 1,000,000, gravity will win. The core will collapse. And another gamma ray burst, perhaps as powerful as the boat or more so, will fire outward across the universe. In another 1,000,000,000 years or 2 billion years, that beam may arrive at wherever life then exists, and whoever is there to detect it will measure it and marvel at it and wonder about what produced it. We are part of a continuous story. We are not the beginning of it, and we are not the end. We are one chapter in an enormously long book, a book with no author, but with laws and with beauty and with the consistent capacity to surprise. Every generation of scientists has discovered that the universe is stranger and larger and more intricate than the previous generation imagined. And every generation has found that the more they learn, the more questions open up. The universe is not running out of mysteries. It seems, if anything, to be generating them faster than we can resolve them. And that is not a frustration. That is an invitation. An endless invitation, written in light, extended to every curious mind in every generation, forever. You have been part of that tonight. You have traveled, in your mind, in your imagination, in the soft space between waking and sleep, from the Big Bang to the present, from the birth of the first stars to the most powerful explosion ever detected, from the quantum foam of the early universe to the vast, dark, expanding reaches of the cosmic web. You have visited black holes and neutron stars, and gamma-ray bursts and nebulae. You have learned something of how time bends, and how gold is born, and how the universe you live in came to have the shape it has. And now it is time to rest. Let your thoughts drift the way clouds drift on a still summer day, slowly, without direction, changing shape without purpose, until they dissolve entirely into the blue. Let the images of galaxies and exploding stars grow soft and distant in your mind, like lights glimpsed through fog. Let the numbers, the light years and the joules and the billions of years, lose their edges and become simply a feeling of vastness, of depth, of being embedded in something immeasurably large and immeasurably old, and, in some quiet way, immeasurably kind. You are safe. You are warm. You are held by gravity on a small and beautiful planet that has been circling its star for 4.5 billion years without interruption, spinning steadily through the night, carrying you with it, always and without effort, through the dark. The stars are above you right now, or below you, or beside you, depending on where you are on the turning sphere of the Earth. They are always there, whether clouds hide them or daylight washes them out. They are always burning, always sending their light outward in all directions, some of it reaching your world, some of it reaching worlds you'll never see. The universe is always broadcasting, always offering its light to anyone with the instruments to receive it. You received it tonight. You listened. And now, let yourself go. Sleep well, dear traveler. Dream of light crossing distances too vast to name, arriving after billions of years at somewhere warm and quiet. Dream of nebulae glowing in slow, silent colors, red and blue and gold, in the space between the stars. Dream of galaxies turning at the edges of the observable universe, their light still making its way toward us across the dark. Dream of the boat, that ancient, overwhelming explosion in a faraway galaxy, its energy long since dissipated, its black hole now quiet, its message delivered, its story told. You are made of that story. You carry it in every atom of your body. And tonight, those atoms are resting, and the universe is resting with them in the quiet dark, in the slow and patient turning of the world. Thank you for spending this time with us here on Dreams of Gravity. It is always a privilege to travel through the cosmos with you. Wherever you are tonight, whatever city, whatever season, whatever hour surrounds you, we hope this journey brought you a little peace, a little of the vast and humbling quiet that the universe offers to anyone willing to look up and wonder. Good night, sleep among the stars, and we'll see you next time.